Let's properly break down this paper. Efficient memory management for LLMs serving with PagedAttention, the work behind vLLM. And by the end, you'll understand every moving part, from the attention math to the operating system trick at its heart. Serving a language model is shockingly expensive. A single request can cost 10 times a web search. And here's the strange part. You're usually not even using the GPU's compute. You're starving on memory. This paper doubles to quadruples serving throughput on the exact same hardware by borrowing the oldest trick in the operating system's book, virtual memory with paging. We're going to build the whole thing up, why the memory fills, exactly how it gets wasted, the paging system that fixes it, how sequences share memory, and how it all holds up under load. Start with how generation actually runs. A language model is autoregressive. It produces one token at a time, and each new token is conditioned on every token before it. That splits serving into two very different phases. The prompt phase reads your whole input at once. One big parallel matrix multiply. The GPU is saturated and happy. Then the decode phase grinds out tokens one by one. Each step is a skinny matrix vector multiply that barely touches the GPU's compute. That second phase is most of the wall clock latency, and crucially, it's memory-bound, not compute-bound. It's worth seeing why that decode phase wastes the GPU. Arithmetic intensity is the ratio of math to memory traffic. In the prompt phase, you multiply big matrices, reusing each loaded weight across many tokens. High intensity, the GPU's happy place. In decode, you process a single token at a time, so you stream the entire model's weights in from memory just to do one skinny multiply, then throw them away. Almost no math per byte moved. The GPU's thousands of cores sit idle waiting on memory, serving lives in this low-intensity regime, which is exactly why memory, not flops, is the thing to optimize. So look at attention, where that memory comes from. For each token, you build 3 vectors, a query, a key, and a value, by multiplying its hidden state by 3 learned matrices. The new token's query is dotted against the key of every previous token. Softmax those scores into weights, and the output is the weighted sum of all those tokens' value vectors. The consequence is the whole ballgame. To generate token number 8000, you need the keys and values of the 999 tokens before it. Make it concrete with 3 tokens. Token 3's query dots with key 1, key 2, and key 3, giving 3 raw scores. Softmax turns them into weights that sum to 1, say a little on the first token, a lot on the second. The output is that weighted blend of value 1, value 2, and value 3. Now notice, keys 1 and 2 and values 1 and 2 were already computed back when we processed those tokens. Recompute them every step and cost explodes quadratically. So we stash them. That stash, every past token's keys and values, at every layer, is the KV cache. And the KV cache is enormous. Work it out for a 13 billion OPT model. One token's KV cache is 2, for key and value, times the hidden size 5120, times 40 layers, times 2 bytes for FP16. That's 800 kilobytes. For a single token. A 2048 token sequence needs 1.6 gigabytes of KV cache all by itself. On a 40 gigabyte GPU, once the weights are loaded, you have room for only a few dozen sequences at once. That ceiling on concurrent sequences is your throughput ceiling. And it scales brutally with model size. Bigger models have wider hidden states and more layers, so the KV cache per token grows with them. Tens of kilobytes becomes hundreds, becomes over a megabyte per token as you climb from a few billion parameters to the hundreds of billions. So the exact regime where you most want high throughput, the biggest, most expensive models, is where a single sequence eats the most memory and the fewest fit at once. Memory efficiency isn't a nicety here. It's the whole economics of serving. Here's the whole memory budget on a 13B model on an A100. About 65% is model weights, frozen in place, all serving long. Nearly all the rest is KV cache, dynamic and per request. And the hardware trend makes it worse. From A100 to H100, compute more than doubled while memory capacity barely moved. So compute keeps racing ahead, and memory is the wall that isn't moving. The entire game reduces to one thing. Fit more KV caches in memory, batch more requests together, get more throughput. Why batching? Because all requests share the same model weights, so if you run many at once, the cost of streaming those weights in from memory is amortized across the whole batch. The trouble is requests arrive at different times and finish at wildly different lengths, so naive batch-level scheduling stalls everyone on the slowest member. The fix that became standard is iteration-level scheduling. After every single token step, finished requests drop out of the batch and waiting ones join. It keeps the GPU busy, but it still slams into the memory wall because the number you can hold at once is set by the KV cache. Take Orca, the strongest prior system. Its iteration-level scheduling was a real advance. No padding, requests flowing in and out every step. But for memory, Orca still does the old thing. It stores each request's KV cache in one contiguous tensor, and because it can't know the output length, it reserves a chunk size to the maximum. So its scheduling is modern while its memory management is stuck in the past, and that mismatch is exactly the gap vLLM walks into. And how well was that memory actually used? Badly. Here's where 2/3 of it vanishes. Because deep learning frameworks want tensors in one contiguous block, old servers hand each request a single slab, and not knowing the final length, they reserve the maximum, say 2048 tokens, up front. 3 distinct wastes follow. Reserved, slots you truly will fill later, but that sit idle now, blocking other requests from using them. Internal fragmentation, a request that ends after 10 tokens still holds all 2048. The other 2038 slots are pure, permanent waste. External fragmentation, the odd-sized gaps the memory allocator leaves between differently sized slabs, which no request can ever use. Add reserved plus internal plus external, and most of your KV memory is doing nothing. This is a solved problem. Every operating system faces the identical shape of it. A program wants one long contiguous address space. Physical RAM is a patchwork of scattered free scraps. The classic fix is virtual memory with paging. Chop memory into fixed-size pages. Let a program's contiguous logical pages map to physical pages that live scattered anywhere through a page table, and allocate a physical page only when the program actually touches it. The paper's mapping is precise. KV blocks are pages, tokens are the bytes within them, and each request is a process. That analogy is the entire method. So here is PagedAttention. Partition each sequence's KV cache into KV blocks. Each block holds the keys and values for a fixed number of tokens, the block size B, say 16. Now rewrite attention to operate block by block. The query dots against a whole key block at a time to produce that block slice of attention scores. Then the output is the sum, over all blocks, of each value block weighted by its scores. It is mathematically identical to ordinary attention, same numbers out, but the kernel fetches each block separately, so the blocks never have to sit next to each other in physical memory. That single change is what unlocks everything else. Managing those blocks is the KV block manager, and it is quite literally a page table. Each request owns a list of logical KV blocks, numbered 0, 1, 2, filled left to right as tokens arrive. Physically, those blocks live wherever there's free room in GPU memory, in any order. A block table, one per request, maps each logical block to the physical block that holds it, and records how many slots in that block are currently filled. Separate the logical view from the physical reality, and you gain the superpower the old systems lacked. You can grow a request's KV cache on demand, block by block, without reserving a single slot in advance. Watch it decode, step by step. A 7-token prompt needs 2 blocks of size 4, logical block 0 and 1 map to physical blocks 7 and 1. The second block has 3 slots filled and 1 free. First decoded token arrives. There's room in that last block, so its key and value drop into the free slot, and the block table's filled count ticks from 3 to 4. Second token. Now that block is full, so vLLM allocates a fresh physical block, say block 3, points the next logical block at it, and writes there. Blocks are handed out exactly when a token needs one, and never a moment before. No guessing the length, no reserving the max. And that is what kills the waste. Because blocks fill strictly left to right, and a new physical block is allocated only once the previous one is completely full, the only unused space in an entire request is the tail end of its very last block, at most a handful of slots. Internal fragmentation shrinks to under 4%. External fragmentation disappears entirely because every block is the same size, so any freed block fits any need. Utilization climbs from that dismal 20 to 40% up to about 96. Turn that into throughput, because that's the whole point. Suppose your old server was genuinely using only a third of its KV memory on real token state. vLLM uses nearly all of it. Same physical memory, roughly 3 times as many sequences resident at once. And since serving is memory-bound, more concurrent sequences is more work done per pass over the waits. That translates almost directly into multiples more throughput at the same latency. The 2 to 4 times headline isn't a new kernel making math faster. It's simply fitting the request you already had into memory you were already wasting. And multiple requests just coexist in one shared pool. 2 sequences logical blocks map to physical blocks interleaved anywhere in the same GPU memory region. Request A's block might sit right between 2 of request B's, and neither cares, because each follows its own block table. When a request finishes, every one of its physical blocks frees instantly and returns to the pool for whoever's next. Memory that used to be locked up for a sequence's entire lifetime now churns freely, like a well-run heap. This is the part where, if you enjoy watching a serving system get an operating system upgrade, you hit like and subscribe. It genuinely helps. Because now we reach the payoff the old contiguous world simply could not touch, sharing memory between sequences. The enabling mechanism is one number per physical block, a reference count. How many logical blocks currently point at it? Allocate a block, count is 1. Point a second sequence's logical block at it, count is 2. Free one reference, it drops back to 1. Drop to 0, and the block returns to the pool. It's exactly how shared memory and garbage collection work in an operating system, and it's the bookkeeping that makes safe sharing between sequences possible at all. Start with parallel sampling. Ask a coding assistant for 5 completions of one prompt. All 5 share the identical prompt, so why store its KV cache 5 times? In vLLM, all 5 sequences' logical prompt blocks map to the very same physical blocks. Those blocks' reference count is 5. Then generation diverges. The instant one sample needs to write into a shared block, vLLM sees the reference count is above 1, copies just that single block, decrements the original's count, and lets that sample scribble in its private copy while the others keep sharing the rest. That's copy on write at block granularity, the exact trick that makes forking a process cheap. Beam search pushes this much further. The beams don't just share the prompt. They share most of their generated history too, and the sharing pattern churns every single step as beams branch and get pruned. In a contiguous world, you would be copying gigantic KV tensors around constantly just to keep beams organized. With paging, it's all pointers and reference counts. Shared blocks stay shared. A beam that diverges copies exactly 1 block, and a pruned beam simply decrements counts, freeing whatever no beam points at anymore. The paper measures up to 55% of the KV memory saved on beam search this way. The same mechanism nails shared prefixes. Picture a long system prompt, or a fat block of few-shot examples, that every single user request begins with. Store it once as a set of physical blocks, and point the first logical blocks of every request at those shared blocks. 100 requests, 1 physical copy of the shared context. Sharing within a request, and sharing across completely separate requests, both fall straight out of the same page table and reference count machinery. The sharing is not a rounding error. Now the hard case. Requests keep generating, their KV caches keep growing, and the GPU runs out of memory mid-flight. vLLM schedules first come first served, and under pressure it preempts. The key design decision is that preemption is all or nothing per sequence, because you need every one of a sequence's blocks together to take even one more step for it. There's no point evicting half. vLLM evicts a whole sequence's blocks at once. It preempts the most recent arrivals first, lets the older requests finish and free their memory, then brings the evicted ones back. How do you bring an evicted sequence back? Two options. Swapping. Copy its KV blocks out to CPU RAM, then copy them back into the GPU when room opens up. Or recomputation. Throw the KV cache away entirely and simply regenerate it from the sequence's tokens in one fast, parallel, prompt-style pass the moment the sequence resumes. Which wins depends on the block size and the GPU to CPU link. Small blocks favor recomputation, since swapping tiny chunks is all overhead, while large blocks favor swapping. vLLM implements both and picks per situation. Scale past one GPU, and the design still holds cleanly. vLLM keeps a single, centralized KV cache manager and scheduler, one brain. The model itself is split across workers with tensor parallelism. Each worker owns a slice of the attention heads, and therefore stores the KV cache only for its own heads. But all workers share the same logical block table. Every step, the central scheduler broadcasts the block mapping instructions. Each worker runs PagedAttention on its local physical blocks, and the whole cluster's KV cache stays in perfect lockstep, with the manager none the wiser that it's distributed. Making paging fast on a GPU took real kernel engineering, because a naive scattered block access pattern can be slower than one contiguous read. vLLM fuses the work into custom kernels. One kernel reshapes freshly computed keys and values and writes them straight into their assigned physical blocks. The PagedAttention kernel fuses gathering the scattered blocks with the attention math itself, so the block lookups hide behind the computation. And the copy-on-write block copies are fused too. The upshot: paging with negligible kernel overhead. You get the huge memory win while barely paying for the indirection. One more detail on why block size matters at the hardware level. Within a single KV block, the token's keys and values are laid out contiguously, so the GPU reads them in one fast, coalesced burst. The memory system loves that. The only non-contiguous jumps happen between blocks, and there are few of those. So a block is a unit of contiguity you keep, wrapped in a flexibility you gain. Make blocks too small, and you take too many jumps and underuse each read. Too large, and the last block waste creeps back. That tension is exactly what the Ablations pinned down. To the numbers. They evaluate OPT at 13, 66, and 175 billion parameters, plus llama, 13B, on real request traces, ShareGPT, which has long, chatty, variable conversations, and Alpaca, which is short and uniform. The baselines are the strongest systems of the day, faster transformer, and Orca in 3 flavors, including an Oracle version that magically knows each output's length in advance, so it can reserve perfectly. The metric is normalized latency versus request rate. Essentially, how hard can you push the system before per token latency blows up? On basic sampling, vLLM sustains a substantially higher request rate at the same latency across every model and both traces. The latency curve stays flat and low right where the baselines shoot up and fall over. The advantage is largest exactly where memory is tightest, on the long sequence ShareGPT trace, and on the bigger models where the KV cache dwarfs everything else. And this is throughput bought purely by memory management. The model, the math, and the outputs are all bit for bit identical. The headline, in their words. And the sharing scenarios widen the gap further. Parallel sampling and beam search are precisely where the old systems duplicate KV cache they never needed to. So they're precisely where vLLM's copy-on-write pays off most. And the throughput advantage grows as you ask for more samples per prompt or wider beams. A heavy shared system prompt tells the same story. The rule of thumb: the more sharing a workload contains, the more paging wins, because vLLM is the only one of them that can actually exploit it. Now the ablations that pin down the design. Block size first. Too small, and the kernel can't process enough tokens in parallel per block, so it underuses the GPU and pays too many between block jumps. Too big, and internal fragmentation creeps back. That half-empty final block gets expensive when a block is huge. Sweep it, and the sweet spot in their experiments lands at 16 tokens per block, Enough contiguity for the hardware, little enough waste to keep utilization high. And the recovery ablation, swapping versus recomputation, measured head-to-head. For small block sizes, recomputation wins clearly. Shipping tiny blocks back and forth over the PCIe link is nearly all overhead, so it's cheaper to just recompute. For large blocks, swapping pulls ahead. Across the practical middle, the two are close, which is exactly why vLLM keeps both in its toolbox. In practice, neither preemption path is a real bottleneck. It's fair to name the costs. Paging adds a block table lookup and a bit of bookkeeping on every access, and the fused kernels exist precisely to hide that. It isn't free, just cheap. Copy on write means an occasional block copy when sequences diverge. And none of this speeds up the compute-bound prompt phase. Paging is a memory management win, aimed squarely at the memory-bound decode phase and at fitting more sequences. Those are modest prices for 2 to 4 times the throughput, but they're real. So the whole system, top to bottom. Serving is memory-bound on the KV cache, which grows with every token and every request. Old servers waste 2/3 of that memory on contiguous, max-length reservations. PagedAttention chops the KV cache into fixed paged blocks with a per-request block table and allocates them on demand, cutting waste to a single block. Reference counts and copy on write let sequences share blocks for parallel sampling, beam search, and shared prefixes. A preemptive, all-or-nothing scheduler with swap or recompute handles overflow. Fused kernels make the indirection nearly free, and it all distributes across GPUs under one central manager, for 2 to 4 times the throughput on the very same hardware. Which leaves the thought I can't shake. The single biggest LLM serving win of its year wasn't a change to the model at all. It was someone reading a 1960s operating systems textbook and noticing the KV cache is just virtual memory. So how many more GPU bottlenecks are really just classic systems problems wearing a fresh coat of paint, waiting for someone to recognize them? That's my read. Tell me yours. Until next time.